All right, it looks like I'm back online. I think maybe there was a problem with my microphone last time. This live stream software can be a little bit finicky because there's a lot of things you have to make sure are working right when you go online. And I'm a little bit still fresh with it, so I'm not always checking things perfectly. I just want to confirm that everything is working before I start doing something here. Yeah, it looks like we're okay. It looks like the chat thing is working. So yeah, I had a bit of a shorter session this morning just because I had some work I had to do, and that kind of thing happens. I mean, you're not always going to be able to study as much as you want because other things are going to conflict. So that's one of the reasons why I did more last week, because I knew that I had a bit more flexibility in my schedule last week than this week. So I tried to do a little bit more. So this week, I'm going to hope that I can do what I plan to do, but you just have to make do sometimes. Now, I had been working on some of these concepts, so I'd kind of divided up my task for learning between doing some kind of work on concepts, facts, and skills here. And then the other thing was to do work in the going back and doing the problem sets. Now I've done, you can see I haven't crossed out all of these things. A lot of things I haven't crossed out here were facts, and some of these things I just kind of decided not to do them. They're mostly going to be worked on here. And then these two little guys here I don't think are super important for me to do right now. So I might actually be shifting back to working mostly on problem sets again. But I think there's going to be an iterative process. So I'm going to do these problem sets, work on them, and then maybe jump back again. There's some here that are circled that I didn't do at all. So I kind of feel like those are good ones to start with, just because, yeah, I didn't do them. So they're fresh problems to do. And then, well, I guess 1.1 I didn't finish it. I did start it, but I didn't finish it. And so I think I might work on some of those. I think some of them have some stuff to watch, but I figure getting done the ones that I hadn't done at all yet would be good. And then I have actually 100% finished all of the problem sets, at least gone through them. And then I will kind of work down through going through more detail with these. So I'm going to go over and start with question 1.1, which I remember was about the classical model of the hydrogen atom and why that doesn't work. So let me just jump over here. So I can close these. And let's go assignments. Problem set 1. Radiative collapse of a classical atom. So I had been working on this one and I had just gotten stuck. And I don't know whether I'm going to do any better this time because I don't think I've learned anything about this particular problem since then. But I'm going to give it another shot. And if I can't get it, I'm just going to go to the feedback here because this was, this is the solutions. Oops. This was something that I was just finding a little bit challenging here. So we have dE dt is equal to negative 2/3 q squared a squared over c squared. And then this is going to be, so this is 1.1. This is going to be electron charge. So this is, I don't know, QE, I guess. This is the distance. Or this is the acceleration of the distance. What am I doing here? Acceleration. And then this is obviously speed of light. Now, dE dt, this should be force, right? Because energy is equal to force applied over time. So if you take a delta time, dt, hold on a sec, dE dt of this is equal to cancel, and you get force. So this should be a force. So if this is the change in energy over time, this is related to a force. The force is, we can also look at the force compared to so let's work on A here. Show that the energy loss per revolution is small. No. This is force not times time. What am I? I'm crazy. This is distance. Distance. Going crazy here. All right. Energy loss per revolution is small compared to the electron's kinetic energy. Hence, it is an excellent approximation to regard the orbit as circular at any instant, even though. Thanks, Andrew. To regard the orbit as circular at any instant, even though the electron eventually spirals into the proton. So yeah, we did this one before. So basically, they're just, oh, that's a really terrible circle. Basically, they're just trying to show this, that this width is so small that it's negligible and we don't have to really consider it that much. So the classical atom is a stability problem. How big is this effect? So this was the thing. We needed to figure out what the speed was so we can figure out the kinetic energy, and then the amount that you lose is low each time. Have I learned anything since then? Well, the classic idea is that there's a force experienced here. And so that force is going to be related to this. How fast is it going? That's the question. I know we looked up the gravitational ones for circular orbital velocity. And I remember being that I couldn't use them because in gravity, mass is like the charge, but mass is also a part of the F equals ma. So I'm worried it was going to cancel there, and I wasn't going to be able to just apply that formula. I'm trying to think if anything comes to mind for how to solve this problem now. I know this is basically just classical physics, so I'm just trying to think of what's the right way to solve this. So what is our Coulomb force? We have our Coulomb force, and that's creating an acceleration. And then how do we take this acceleration and figure out what the circular orbit is going to be for that? I want the exact formula. Coulomb's law. There we go. So yeah, it's going to be KE, and I'll just write that down. KE. And this is F is equal to KE QE squared over R squared. This is the force. And the question is, what would be the velocity for a stable orbit if we didn't include radiation? What other ways can we get this? I think, can we do kinetic energy equals potential energy? Is that going to solve the problem? Because that would be conserved, right? So our potential energy is equal to what? How many volts would that be? That would be do we want P equal to KE for this? Hey, knowledge 543. Joules per Coulomb. Oops. So the potential is going to be force times distance, but the distance and force are changing. Potential energy is going to be what? Integral from like 0 to r. And then the force is this. R naught. R. And then this is dr, right? Oh boy. I think it's this dr, right? And then this would be 1 over r squared is going to be negative. So 1 over r. And then evaluated at r naught. So we can let's call this r right here. That should be right. So this should be the potential energy is equal to the kinetic energy, 1/2 mv squared. And how much is being lost here? Per revolution. Let's figure out this first. This should be Ke QE squared divided by R mass electron. Can I figure that out? What would that be? Let's go. Oh, I'm not on the prompts anymore. People ask me how long do I have planned? Well, I'm only working on this for another week, so not too long. Okay, so this one here is we've got what did I work out for this? I wrote it down here. Okay. So root of 2 times 9 times 10 to the 9th. And then this electron charge. Um, 1.6 times 10 to the negative 19. Don't know this radius. So I'm going to have to put it over here. I guess I don't want it like that. Oh, times. And then what is our mass of electron? 9.1 1 times 10 to the negative 31 kilograms. Is this sensible here? We've got newtons per meter squared per Coulomb squared. So what do I have? I've got newtons times, this is Coulombs squared, right? Forgot the square. This is this squared. This is kilograms. What's our units of everything? So hold on a sec. I've got 9 times 10 to the 9th newtons per meter squared Coulomb squared times 1.6 times 10 to the negative 19. Squared, and then this is going to be our electron charge is going to be Coulomb squared. So these are going to cancel. And then we've got kilograms, and we've got meters. So and this is all under a square root sign here. So newtons is force is equal to mass times acceleration is equal to kilograms times meters per second squared. So we've got kilograms cancel with kilograms. Meter cancel with meter. And I've got, what do I have here? This cancels with this, no? No, this is over meter squared, no? So I have, is this meter squared per second squared? This is, where's our second squared? Our second squared is here, so that's underneath. What do I have here? I have, hold on a second, let me just write it again. Kilograms Let me just write it all out here. So this is going to be kilograms times meters times second to the minus 2 times meters to the minus 2 times Coulomb minus 2 Coulomb squared. So it's going to be minus 1. And this is times kilogram minus 1 meters. I got meters. That doesn't look right. This one, Coulomb's constant. No, it is meter squared over. Hold on a sec. Times meter squared. So the meter squared is up here, which should be right. Yeah. And then this becomes meters squared, and then this is meters to the third. Kilograms, meters. So this becomes meters, and this becomes meters squared. So this becomes, I can cross this with 3. And we have now 2. And then we have equals meters per second. Okay, so we do have a velocity. Dimensional analysis works. All right. But of course, it's defined in terms of an R. So that's going to be, what do we have? Root of 2 times 9 times 10 to the 9 times 1.6. 1.6 times 1.6 is I think it's going to be 2 something. Where's my phone? Oh, I don't have my phone here. Let me just, I'll just do it quickly on the calculator here. I cannot find the calculator for the life of me. Here we go. 1.6. 2.56, yeah. 2.56 times 10 to the negative 38 divided by 9.11 times 10 to the negative 31. So 31 is going to cancel with 7 of these here. 7 is going to cancel with this, so we're going to get 7, and then this is going to be 2, and then we're going to have 9. You just cancel this. It's 1, 4 point. This is going to be about 5. 5 divided by 1.1. 5-ish. So this is going to be roughly 5 times. This is 500 over root R is equal to V. And then how much is the velocity lost, or how much energy is lost each rotation? So we've got, this is the velocity. The rotation is going to be, so dE dt is equal to minus 2/3 q electron squared. Acceleration is what? Acceleration is going to be this F equals ma divided by the mass. So it's going to be this ke divided by mass electron c squared. So this is going to cancel this, and we're going to get equals negative 2/3 ke over mc squared minus 2/3 9 times 10 to the 9th over 9.11 times 10 to the negative 31 times 3 times 10 to the 8. Get this 1. This is going to be minus 8 is going to make this 23. 23 minus 9 is going to be 14. So it's going to be 3, 9. And we have is 3.33. So this is 10. So we can just cancel off another 3 here. This is going to be 2 times 10 to the negative 13. This is joules per second, I guess. And if that's joules per second, well, what's our kinetic energy? I guess I don't need the velocity here. So our kinetic energy here is this 1/2 mv squared, which is going to be equal to the potential energy, which is going to be equal to 9 times 10 to the 9th QE. Or did I write that down? (1.6 times 10 to the negative 19 squared over, oh, this is the radius. We don't know the radius. I forgot an r squared here. That is bad of me. So hold on a second. Let me write this out in terms of kinetic energy is going to be equal to potential energy, which is equal to KE QE squared over R. And then that's equal to, so I'm going to put 1/2 mv squared is equal to this, which is equal to This is our kinetic energy. No, these aren't an equality. I don't think I can eliminate it here. Then we've got, so what did I do wrong here? I had QEQM. Oh, and I forgot the r squared. So that's also an r squared here. So I can just put divided by r squared. All right, and so we have I think I need to know the r just because I'm gonna just guess the r here. I think they put it in the question, don't they? Equal size and imagine 1 extra. One times 10 to the negative 10. So this is going to be equal to 2 times 10 to the negative 13 by 10 to the negative 10 squared. 13 is 20. Negative 33. This is joules per second changed. And what's our total kinetic energy? Is kinetic energy, yeah, I did this divided by radius, which was so this is going to be times 10 to the negative 1. Then we're going to have 9 times 1.6 times 10 to the negative 38 minus 1 is minus 39, which is equal to 9 times 1.6, 9 times 8 times 2, 56 times 200. You know what, I'm just going to do it again on calculator real quick. Where'd my calculator go? Oh, here it is. or 1.44 times negative 38. And this is the time loss per second, or energy loss. So it's going to take to remove all this kinetic energy. Now each time it's going to lose energy. I've got to integrate somewhere here. Well, at least I can say we know the velocity is now going to be this thing here, but we have the radius. So let's try to figure out 1 over this is, so now this is root 10 to the negative 10. So this is root 500 times, or divided by root of 10 to the negative 10. So it's 10 to the negative 5. And this is 5 times 10 to the 2. So we've got velocity is equal to so 500 times 10 to the 5th, right? So we've got 5 times 10 to the 7th. So it's close to the speed of light. So we're going around super fast. I think that's all I can really say right now. Speed equals this right here, right? And the all right, I'm gonna go jump over. I think that's about as far as I can get right here. So let's see. This seems like circular logic was actually so let's see what they had. They had here q squared over r squared is equal to mv squared. For mr, and what did I have for q squared? Or what did I have for v? I had v. So my answer, I'll put my answer in pencil. My answer was v is equal to square root of q squared divided by m divided by r, and plus the constant. So, okay, that was right. The kinetic energy is given 1 half mv squared equal to 1 half mv squared, which is equal to q squared over 2r. Right, okay. 2r. Oh, right. Yeah, because there's the 2 there. Okay. This to the energy loss per orbit. The Larmor formula, on the other hand, gives us the energy loss per time. So you need to figure out the orbital period of the electron. Angular speed of the electron per electron. So assume the lower circus, we can take the orb. Assume this means that time for any one orbit is given by 2 pi r divided by v. So okay. Is equal to d t minus 2/3 q squared a squared c cubed. I wrote that formula down wrong. Is it cubed? Ah, cubed. Okay. V squared over r squared. 2 pi r over v equal to 4 pi 3 q squared r v over c cubed. Okay, so I didn't, I forgot to use this idea of figuring out the orbital period, which, I mean, is important, but I got a lot of the other things right, which I hadn't the first time, so that's progress. Let's go forward with B then. Using the typical size of an atom, 1 angstrom, a nucleus, 1 femtometer, calculate how long it would take for the electron to spiral into the proton. So I think I'm going to have to use some integrals now, because what's happening is we're having the electron is kind of doing this, like it's spiraling in like that. And then the question is, how long does that take? Okay. So our kinetic energy is equal to let's try to model what's happening here. Can I just count the number of... They're going to go faster as they go in, so that's not going to help. Well, if they go faster than it's in, I don't know whether that would that make any difference here? So let's go here. We got our dE dt minus 2/3 q squared a squared c cubed which I wrote as squared before, which is annoying. And then this is how much energy is lost. And then we have a total energy, but this acceleration is changing each time. That's what we have to integrate. So there's some function of kinetic energy is equal to Q squared over 2R. Excuse me. Oh, I thought I could sneeze there. Oh. All right. How can I relate these? So we've got the R here, but there's going to be an R here for this acceleration. So let me just write this out. Minus 2/3. Q squared F equals MA is going to be. So this is force divided by mass squared. C cubed is equal to minus 2/3 Q squared. Force is Q squared over R squared. Times mass squared. C squared. Is that right? These guys cancel. M squared. R squared. E squared. And you know what? I'm just going to go sharpen my pencils quickly. They're looking really dull. And I'll be back in just 1 second. Do I have my sharpener here? Oh, here we go. Okay, let's try again here. It's some kind of integral here. I'm just trying to think what it would be. Well, let's think through real carefully what's happening. So each time we go around, we're losing a little bit of energy. And when we're lower here, closer to the electron, the force is stronger. We are moving faster. And we are radiating even more energy. So this is an accelerating kind of process. And then the question is, how long does it take to go through all the way down to the bottom? So for each sort of step in the process, we have, so I would put like time, so let's see, time to go around once is equal to what? Well, we have our velocity, and it has to cover 2 pi times the radius. This is the time to go around. And after you've gone around once, if we just assume that the radius is a little bit smaller. And the force is a little bit bigger. And you've left off a little bit of energy, so the velocity is a little bit higher. So we have our kinetic energy, and then you lose a bit. Of kinetic energy, and we get our new kinetic energy. And then the question is, how many times does it take to go down to the bottom? Yeah, I'm trying to set it up as some kind of integral, or I'm just trying to think. There's a lot of facts here, and I'm just trying to put the logic in together. So we have some time to, like, this is the amount of time that it takes. So this is, I'm going to put t once is equal to this. This is our time to go around one time. Now we're going to go around a bunch of times till we hit this. And each time we're going to be going around a little faster. So this v is going to change. So this is going to be a constant. So we want to go until r equals 0. What if I were just, this is doing a series is probably not the right way to do it, but it might give me some intuition of how the function is changing over time. So we have 2 pi times, let's start with our starting point, 10 to the negative 10. And our velocity is equal to, this is actually going to be ke 1.6, yeah, 10 to the negative 19 squared. Hold on a sec. over mass, which is 1.11 times 10 to the negative 31. And then this is our times 10 to the negative 10. So this is our starting revolution. So let me see if I can, do I want to put this in numbers right now? Let's just leave it in blank. So let's just go. So it's going to be 2 pi, I'm just going to call it R naught. R naught KEQE squared over M R naught. So this is length of time once. And then we're going to add to that the length of time for the second time around. But the second time around, we've lost some energy. And how much energy have we lost? Well, it was kinetic energy went down by, how much did we lose our kinetic energy by? E loss is now equal to minus 2/3 Q squared A squared, but we can simplify this because the Q squared and A squared is going to, Q squared is going to cancel, so it's going to be minus 2/3 1 over M squared R squared, not kg squared, C cubed. This is our kinetic energy loss in each per transit, right? No, this is, we have to times it by the amount of time. This is per time. So let's see if we go 2 pi R naught over KEQE MRO. And then this is times 2/3 1 over M squared R squared C squared. So this is the total energy lost. What's the right way to look at this? So let me write it this way. We've got dE dt this is our change in energy, and we want a time. So the change in energy is equal to thirds. don't want an energy, though. I want a total time. I don't think that's going to help me either. What else could I try? Maybe I can try breaking down the problem a different way here and see how it might integrate. Oops, I'll take the sweater. So if we look at our kinetic energy over time, total energy, hold on a sec. Kinetic energy is going to be increasing. Total energy is going to be going Matan says, well, I'm trying to understand if we have some point approaching a center as the angle from the outer circle is increasing. I'm not sure if I understand what you're talking about, Matan. Maybe you could try re-explaining your idea here for solving this problem. I'm changing this here. Because what's happening is our electron is speeding up, so our kinetic energy is going to be increasing. Kinetic energy is going up, but the total energy is going down by this amount that we're losing over time. Yeah, I guess maybe you're right. Maybe we could look at how fast is it going at that central orbit. So like when it's right around the proton, how fast does it have to be going? And how fast is it going here? And we can figure out what's the difference in the kinetic energy here. And the difference in the potential energy. And then that should be equal to the radiation. Is that what we're looking at here? So we've got kinetic energy here, some delta potential energy, and we have like K delta kinetic energy. Delta potential energy minus delta kinetic energy is equal to this total energy lost. And we have a time derivative of the total energy lost. But that doesn't really help us because we're going to be losing energy a lot faster here than, because the force vector is so much higher, so we're radiating a lot more here than in the beginning. So I don't think I can work with that. Hmm. What else could we try? If we calculate just in terms of variables, we might both figure it out. So how much does the radius decrease per revolution? That might be a useful question to ask, because if we know how much smaller this is, this delta R, then that's going to be some function vector from outer circle of the spinning ball. Yeah, I'm not sure, Matan, what you mean by this. The force and direction vector will change in relation to the outer circle. It could be my fault. It could be that I'm maybe just not understanding you. Obviously, I'm struggling with this question myself, but try to solve it on your own, and then let me know whether you, when we get to the answers, whether you get the right thing. So if we can figure out how much it changes per revolution, so what would the delta R be? So that's going to be our kinetic energy. So we have KE0 is equal to Q squared over, was it Q squared over R squared or Q squared over R? It's Q squared over R, or 2R. It's Q squared over 2R. And then we have KE1 is going to be equal to Q squared over so this is going to be our 2 squared over, hold on a second, 2 over R minus delta E is equal to Q squared over R1. I'm going to put R naught here, right? So if I can get dr d what? dt is a function of R. So this is equal to square root of 2R naught minus, what is R? And we've got F over mass Q squared. So this is 1 over R squared. And is equal to so how do we get this in terms of R1? Well, we have 1 over R1 is going to be equal to Q to the 4th minus equal to, so it's going to be 1 over Q for 1 over R naught. Why did I do R naught twice here? 2 R naught. 2 R naught. R naught squared M squared C cubed. So we want to go like dr d something. Dr dt. I still think this is going to work because this is the reduction in energy. But I don't think that it actually I think I'm stuck. I think that's good enough. I'm going to try to see what the answer is. And energy per time, whereas we're interested in change in radius. Therefore, we need to rate energy to the radius. Okay. K plus U is equal to 1/2 mv squared minus q squared over r is equal to q squared over 2r minus q squared over r is equal to minus q squared over 2r. Okay. Oh, I should put this in pen. Oops. Put this in pen right here. Okay. dE dt is equal to d dt minus q squared over 2r squared a squared or c cubed. So we have d dt 1 over r is equal to so we have d dt 1 over r is equal to 4/3 q to the 4th m squared c cubed r to the 4th. Over r squared dr dt equal to 4/3 q to the 4th m squared c cubed r to the 4th. R squared dr dt to minus 4/3 q 4th m squared c cubed and then we're going to go radius initial, radius final, r squared dr dt to minus 4/3 q to the 4th m squared c cubed 0 d0 dt. So basically we took this over to this side and integrated those two. This goes right here. So 1/3 rf cubed minus ri cubed is equal to minus 4/3. And this is just T naught. Yeah. So T naught is equal to m squared c cubed 4q for radius final cubed minus radius initial cubed. 1.1 times 10 to the negative 10 seconds. Wow. Okay. So did not get that one right. This one was tricky. I think some of the things that I'm a little weaker on here. And Tad has a link here for me. Let me open it up a new page here. See, I think well, that's not the approach that they use using the angle. I think the reason why they're not doing that is because we started off with this circular approximation, which makes this easier. But if we look through this, I think the thing that I would have missed is I think this crucial step here of taking ddt this dr dt. Yeah, I think it's just I think just some of these calculus things are just going over my head right now. So yeah, this is very much like 1803 kind of differential equation stuff. Just trying to see if I can understand what they're doing here. I was sort of on the right track of looking at the radius, but definitely didn't get to do this. Well, I will make a note here about differential equations, because this might be something that I have some time to follow up on. Up on these. Okay. All right. With that covered now, let's go and try C to see if we can velocity of the electron at orbital radius 0.5 angstroms. So what was that? V is equal to Q squared over R. I think it's actually KEQ squared over R, which should be what was it? 9 times 2. What's KE? That constant. 9 times 10 to the 9th. And then this was 1.6? Yeah, 1.6. And this is 0.5 times 10 to the negative 10. So 9 times 10 to the 9th times, this is going to be, what did I have, 2.56, negative 38, 5 times 10 to the negative 10. So we have 10 to the negative 37. So 1.2. 1. We can do 4.5 times. Hold on a second. Let me just do this quickly on calculator. Times 4.6. 10 to the negative 36. No. What am I doing? It's crazy. All right, this is add 10, so 19. No, this can't be right. It's got to be going way faster than this. Yeah, I think I just wrote something down wrong here. V should be equal to square root of KEQ squared over MR should be equal to root 9 times 10 to the 9th times 1.6 times 10 to the negative 19 squared over mass of the electron, which is going to be to the negative 31. What is that, 1.6? What is that? Mass of the electron is 9.11. 10 to the negative 31. And then the radius is going to be times 0.5 times 10 to the negative 10. All right. And let's do a quick check here. This KE is in newtons per meter squared, Coulomb squared. So we have newtons is going to be, newtons is equal to kilograms times second squared. F equals MA. I think I can just cancel the newtons. Hold on a second. This one is dimensional analysis. Quickly, we've got root of newtons times mass squared divided by Coulomb squared times Coulomb squared over kilograms times meters. Let's get meters. One of those cancels. Kilograms cancels from here, and we've got meters per second squared. Where did I lose this? Where did I lose a second? Oh, no. It's 4. No, it's supposed to be radius. No. Hold on a sec. There's definitely a second squared down below, but there should be meters squared up top. Newtons times meters squared, so newtons is kilograms. F equals MA. Newtons squared. Times meters squared is meters cubed. Oh, right. So it's minus 1, so this is going to be squared. Second minus second squared. Yeah, meter second. Okay. And what do we have here? And this is going to be negative 38. Plus 9 is negative 31. This is negative 41. And we thus have square root of 1. 1.5 is going to be 1.6 divided by, as this to 1. So this is roughly double this. So let's say this is like 3 root 3. Yeah, this is like root 3-ish times 10 to the 5th. Is that what we're looking at? Hmm. To the 5th. So 3 times 10 to the 8th. It's like what, 1/200th speed of light, something like that. So probably not. No, I've got 3 times 10 to the 5th. That's centimeters. This looks about right though. 2.3 times 10 to the 5th. So their answer is 2.3 times 10 to the 6th meters per second. I must have dropped one somewhere. Where did I drop one? Oh, this is supposed to be 2.56. Maybe I'm not supposed to use that. I don't know. Okay. Okay, let's do the last one now, D. So the electron approaches the proton. What happened to its energy? Is there a minimum value of the energy the electron can have? No. All right, 1.1 is done. I'm gonna make some notes for. So where's my big sheet of concepts that I want to work on? All right. So we did 1.1. I'm going to cross that off here. I'm going to do 1.5. I think this one I had to watch something. And you know what? Now might be a good time to do that. So let's see. 1.5. I did have 1.4 I wanted to redo. Yeah, watch this video on matter waves. So let's download this right now. Can I download this? Oh, it's downloading. Okay, well, I'm going to just take a quick few second break while this is downloading right now, and I will be back in 2 seconds. Let's get a little water here. So this is taking a little bit longer to download than I thought it would. So I think I still wanted to tackle 1.4 again. Ah, yes. Okay. This is the double slit interference of the electrons. So let me just block this up. 1.4. And then I will try 1.4 and then work over on 1.5 again. So A. What is the distance omega between adjacent maxima of the interference fringe pattern formed on the screen? A distance d beyond the slits. All right. Okay, so this is our setup. And let's see if I can remember how this works. So we've got this is our d. This is our little d. And we want omega, which is going to be our interference fringe. So between adjacent maxima, so let's just say this is like this. So this is right down the middle. What's this, the angle or the distance? Distance. So this is omega. Now, I seem to remember that this, do I need d much longer than little d to make this work? I don't know. So I don't know whether there's going to be a small angle approximation. I'm trying to remember how this goes. So essentially, I think if I can remember, let me see if I can set up the geometry right on this. I have to draw this carefully because it can get messy otherwise. So this is our back of the wall. And I'm just going to put this here. So here is where they're going to both constructively interfere. And the second one is going to be one wavelength longer than it is for this one. So this length of this is going to be length plus this. So the second one is going to be this lambda longer than this one. So I think the way that it worked is if we imagined the plane waves emanating from this one. So this is our lambda. And so this L and L are equal. We have some D. What was the way we did this? See if I can remember how to do this problem. I remember I was not setting up the trigonometry right last time. So I remember that was my issue. Now the question is, what's the right way to set up the trigonometry? Because once you set up the trigonometry, it's actually not a complicated question. Once you get the triangle set up properly. This is our D. Let's say this is theta. This is a triangle of height D here. This was the wrong way to do it, I remember. Did I get the video? Did the video download? Okay, yeah. Video downloaded on this one. Let's put a pin in 1.4 and let's look at 1.5. Because there was a video to watch for that one. So I'm going to open this. Matter waves. What is this going to open with? DLC. Okay. All right. This is, how long is this video? It's about half an hour. Okay, so let's just watch this video. That'll be a good activity to do. Okay.
I hope you got over the shock of learning that light, an electromagnetic wave, behaves in some ways like a stream of particles, the photons, because I'm about to ask you to absorb another punch. I'm going to try to convince you that particles of ordinary matter, behave in some ways like waves. I don't mean by this that the particles bob up and down. They do that sometimes, of course, but that's not what I mean. I mean something much more fundamental. You'll pay a visit to this apparatus in this film, and I hope you'll be convinced by what it shows you that a particle can behave like a wave in a very deep-seated way. Maybe after the first punch, about the particle nature of light, the second, about the wave nature of particles, won't alarm you too much. If it doesn't, then you have something in common with Louis de Bragg. De Bragg suggested, back in 1923, that particles might behave like waves, and his suggestion grew out of his comparison of the way matter behaves with the way light behaves. He wrote that suggestion into a thesis he was submitting for a doctor's degree at the University of Paris. But if you find the waves of matter harder to take than the particles of light, then you're still in good company. De Bragg's examiners at the university were reluctant to give him a degree for such a fool idea. He got the degree all right, but only because Albert Einstein happened to be visiting Paris at the time and said, look, this isn't such a bad idea. So, and then 4 years later, Davison and Germer in New York City and T.P. Thompson in Cambridge, England, described diffraction experiments they had done, quite independently of one another, showing that de Bragg's idea was right. Now, I think you've studied waves enough to remember that waves can be diffracted. Here, for example, you see waves coming up to the edge of a barrier and bending around behind it, so that the barrier doesn't cast a sharp shadow. In fact, if you put something in the path of the waves, which is no larger than the wavelength of the waves bend around from both sides, and the thing casts no shadow. But if you shoot particles at something, for example, the droplets of paint from a spray gun, the particles either hit the thing or they don't, so that there's always a shadow. This way of casting a shadow, by spraying particles at a thing, is used in an electron microscope. Here's a small something that you want to examine in the microscope. You spray it with electrons. You put the beams of electrons through an electrostatic lens. The lens spreads those beams out. And you let them hit a fluorescent screen or a photographic plate so that you get an enlarged shadow of the thing. Here is a picture taken in an electron microscope of some of the tiny bits of matter that make up smoke. They look, as you might expect, like the shadows of little blocks. But the edges of the shadows don't look sharp. You see light and dark bands in them. The electrons making the picture don't seem to behave quite the way they should if they were simply particles like those drops of paint. Here you see a case of diffraction. Diffraction of particles, the electrons. In making those diffraction bands, the electrons are behaving like waves. You can get the same kind of shadow when you place an object, a razor blade for example, in a beam of light. Now, I'll darken the room for a moment. Here's a small source of light. And when I line it up on that razor blade, you can see a shadow through the screen. Looking closely at that shadow, you see diffraction fringes. These fringes are very much like these other fringes made by electrons passing the edges of the smoke pits. So the electrons seem to be behaving like the light. And you might ask the question, are both the electrons and the light behaving like waves, or are they both behaving like particles? But you know the answer to that one. The bands in the diffracted light come from the interference of the light waves with one another. Looking for interference phenomena like this is the best way we know for finding out whether we are dealing with waves of any sort. So the electrons seem to be behaving like waves here. But it's worthwhile trying to find some way to check that idea. Now let me remind you of the diffraction of light by a ruled grating. Here's a thin sheet of plastic that has very fine ridges and furrows molded into it. Looking at them under a microscope, you see that they are arranged in straight parallel lines. The distance between them is very short, maybe about 20 times the wavelength of light. I have a sheet of that grating held flat under a piece of glass. When I shoot a beam of light at the grating, the ridges and furrows scatter the waves of light, and the scattered waves add up in just a few directions. In most directions, the scattered light cancels out. The ruled face reflects some of the beam back at an angle which equals the angle of incidence, but it also reflects some of the beam in other directions. And in those directions, the angle depends on the wavelength, the color of the light. So in those directions, the light is spread out into a spectrum, with the red light at the outer end of each spot, and the blue light at the inner end. The wavelength of the light is shortest here and longest here. When I use only the red light, by putting a light filter in, you see what the grating does to light at the long wavelength end of the visible spectrum. When I shift filters and use only the blue light, you see that the diffracted spots all shift inward because the blue light has a shorter wavelength. Look at that shift again. Red light, blue light. Now, this suggests that if we want to look for the wave-like properties of matter, we might shoot a beam of matter at a grating and see how the matter bounces back. If it bounces back every which way, then that's just what we expect of particles. But if it bounces back in beams, then we suspect that the particles are behaving like waves. In order to get any useful answers, we have to design a grating with lines whose spacing is comparable with the wavelength we are looking for. But what wavelength are we looking for? In his original thesis, Bragg made a brilliant suggestion. I've already reminded you that light comes in little bundles, the photons. Each photon has a momentum. That momentum shows up whenever the photon hits something, for example. And the momentum, P, of any one of the photons turns out to be given by h over lambda, where lambda is the wavelength of the light and h is Planck's constant. Bragg's brilliant suggestion was that the same relation should hold for the matter waves. In other words, solving for lambda, you expect the wavelength to be given by h over p. This is sometimes called the de Bragg relation. Now let's get some numbers into this, using the units with which we are familiar, meters, kilograms, and seconds. In those units, Planck's constant h is about 10 to the minus 33. You see immediately that we're going to need a pretty small value of p to get a wavelength long enough to deal with. To make the momentum mv small, we want a small mass and a small velocity. An electron has a very small mass, about 10 to the minus 30 kilogram. If you accelerate the electron through a potential difference of 100 volts, you will give it a velocity of about 10 to the 7 meters per second. Then the momentum of the electron will be about 10 to the minus 23. Then de Bragg's relation says the wavelength of the electron will be about 10 to the minus 10 meter, which is about the size of an atom. So you want a grating with ridges and furrows spaced by about the diameter of an atom. Well, that sounds pretty difficult, because, after all, the grating has to be made of matter, and matter comes in atoms. But the thing can be done. Here's a model of what one of the ridges on such a grating might look like. The atoms make little humps along the ridge. And when I put another ridge next to it, spaced by the diameter of an atom, the spacing of the humps along the ridges is as big as the spacing between the ridges. But when I've added many lines of atoms, you see that I've just made another sort of grating. Little humps regularly arranged in a plane. It's a different sort of grating from a simple line grating, but it's a grating all right. That grating is the regular arrangement of atoms on the surface of a crystal, and it's already made for you by the crystal, with just the right spacing to do an experiment with electrons. With a piece of plastic ruled with lines in two directions like this graph paper, I could do the same experiment with light, if the spacings in that grating were comparable with the wavelength of light. Actually, I can get the same result by taking one of the light gratings with lines ruled in this direction and put on top of it a second with lines ruled in this direction. I've done this here, and when I shoot a beam of light at this grating, I get a symmetrical array of streaks. You'd expect that one of the gratings, working separately, would give you streaks in this direction, and the other would give you these streaks. But the cross grating gives you these additional beams, making a square pattern. Now let me use those light filters again to show you what happens to the pattern at different wavelengths. Here's what the pattern looks like when I pass only the red light. When I shift to the filter that passes only the blue light, the pattern keeps its shape, but shrinks toward the center. I'll switch them again. Here's the red, the longer wavelengths. Here's the blue, the shorter wavelengths. Short, long. Now you know what you might look for when we accelerate a beam of electrons by about 100 volts and bounce it off the surface of a crystal. If the electrons are behaving like waves, we expect them to bounce off in beams which make a regular array of spots. And when we increase the accelerating voltage, so that we increase the energy and the momentum of the electrons and shorten their wavelength, we expect the pattern to shrink, like this. And now you're going to visit Dr. Lester Germer at Bell Telephone Laboratories, who has this experiment with electrons all set up. In his researches, Dr. Germer uses an apparatus in which he shoots electrons out of an electron gun. They go through a tube, bounce off a crystal, and come back and hit a fluorescent screen and make spots on it. Dr. Germer is the man who collaborated with Dr. Davison in the earliest experiment that showed the wave nature of matter 35 years ago.
This is the apparatus which has just been described. I use it to study the arrangement of atoms on the surface of a crystal. This is an electron gun. Electrons come from this gun and are brought together into a narrow beam. This beam strikes the surface of a crystal. Some of the electrons of this beam are bounced off from the surface of the crystal at various angles and reach a fluorescent screen. They show on the screen as bright spots. From the positions of these spots, we know the angles through which these electrons were scattered. And from these angles, we can work out the arrangement of the topmost layer of atoms on this crystal surface. In order to see the diffraction pattern made up of these electrons, we must turn off the lights. These switches control the voltages in the electron gun and bring these electrons into a sharp beam. We can now see the diffraction pattern which these electrons make on the fluorescent screen. This pattern was made by electrons having a speed corresponding to 40 volts. It is a symmetrical pattern, has the symmetry of the top layer of atoms of the crystal surface. Now I shall increase the voltage to 47. The pattern shrinks. I decrease the voltage, the pattern gets bigger again. I'm changing the voltage back and forth between 40 and 47. The pattern expands and shrinks. We're using only this small range of voltages because if we go to larger voltages, there are some subsidiary effects which we do not wish to show. The ratio between the sizes of these two patterns is the ratio of the square roots of these two numbers, 40 and 47. This is because the energy of the electrons varies directly with the electron voltage, and the momentum varies with the square root of the voltage. Correspondingly, the wavelength varies inversely with the square root of the voltage. I'm changing the pattern back to 40 volts now. The pattern is bigger again. And now again back to 47 volts with a smaller pattern. I could calculate the wavelength by finding the angles of the beams from the positions of the spots on the screen, and by knowing the spacings of the atoms in the crystal. And this, of course, we do know. This calculation of electron wavelengths is like what Dr. Davison and I did 35 years ago. But our apparatus was not as convenient as this one. We couldn't see diffraction spots on a fluorescent screen. The old tube, which we had at that time, I now have in my office. This is one of our first experimental tubes. We detected reflected electrons by moving a collector around inside this can. How it works is best shown in a sketch. So I have here a sketch of the very first tube which was used. This is the sketch. This is the electron gun. It's a hot filament. The electron beam is defined by these pinholes. The beam hits the surface of the crystal. This is the box which can be moved around to different angles, and we can read the current at different angles just by tipping the whole apparatus. This box moves around under gravity as you tip the tube. Here is such a tube, the gun, and the crystal, and the collecting box are within this metal chamber and can't be seen. But as you turn the tube, this pointer moves around and it registers the angle of the collecting box. So we can measure the current to this collecting box at different angles. In one experiment, we got a result like this. This is a plot of the current through the box as a function of angle. This is the current. This is the angle of the box. There's a strong current coming straight back. We don't measure at angles less than 20 degrees. But from 20 degrees, with increasing angle, the current is decreasing. Then it comes to a new maximum out here at about 53 degrees. Then the current decreases again. If we had had a fluorescent screen, this peak at about 53 degrees would be recognized by a sharp spot on the fluorescent screen. This is a pretty tedious way of observing intensity maximum. It is very much more laborious than our present method of using a fluorescent screen. Originally, we were not looking for confirmation of Broy's theory of matter waves. We were doing these experiments before we had ever heard of de Broy's theory. But as soon as de Broy's theory came to our knowledge, we checked it against the positions and voltages at which our diffraction beams came out, and we found that they checked quite well. After finding the first few sharp beams, we made an extensive exploration and found that there were many diffraction beams and that they checked the Broy theory quite thoroughly and extensively. This was the first experiment in which electron diffraction was observed.
The experiment that Dr. Germer has just described to you is sometimes called the Davison-Germer experiment. Now let me describe to you the experiment that G.P. Thomson did in Cambridge, England at about the same time. Thomson shot a beam of electrons at higher voltages right through a thin gold foil and examined the beams coming out the other side. Now Thomson's gold foil was made of very many tiny crystals, not just one. If we represented one of Thomson's crystals by this square grating, we would have to represent his gold foil by a great many such gratings turned every which way. Thomson's beam, narrow though it was broad enough to hit lots of them. Now I can use my square grating and a beam of light to prepare you to understand what he saw. One of the little crystals might give a set of beams like this, and another a set of the same beams, but all turned in a different direction, and so on. Well, from the whole collection of little crystals, you'd expect the diffracted beams to make the pattern that I get when I whirl this grating around. And here's the sort of pattern that Thomson actually got when a beam of electrons was diffracted by passing through a thin foil. Don't be disturbed by the fact that this pattern is made by transmitted electrons, not by reflected electrons. A transparent grating gives you just as good a diffraction pattern for the light that goes through as for the light that reflects. Of course, in Thomson's experiment, the electrons going through each crystal are scattered by layer after layer of atoms, not only the layer at the surface. But that just means that each electron is scattered by a three-dimensional grating instead of a two-dimensional grating. A three-dimensional grating diffracts a beam of waves in definite directions too. Indeed, light going through a crystal, or through a foil made of many little crystals, is diffracted that way whenever the light has a short enough wavelength, a wavelength comparable with the spacing between the atoms and the crystals. X-rays are light with that kind of wavelengths. Here is a photograph taken by a beam of X-rays shot through a metal foil. The same metal foil that was used for making the other picture that I showed you, taken with the beam of electrons. Comparing those two photographs, you see how alike they are. The electron photograph, the X-ray photograph. The spacings of the circles is the same in both of them. I find this a very convincing proof myself that a beam of X-rays and a beam of moving electrons have something in common, that they both have a wave-like property, The photographs aren't exactly alike. For one thing, the relative intensities of the circles aren't the same. After all, X-rays and electrons aren't exactly alike. X-rays are X-rays, and electrons are electrons, and the atoms in the foil scatter X-rays and electrons with different intensities. But both have a wave-like property, and the laws governing the directions in which they are scattered are the same. Now, de Broglie wasn't talking especially about electrons when he made his suggestion. He thought all particles of matter might behave like waves. And soon after the electron experiments, people devised experiments to show that de Broglie's prediction was correct for other bits of matter too. Here is a curve obtained by Esteban and Stern, working in Hamburg in 1929, with beams of helium atoms. They squirted a jet of helium atoms at the surface of a lithium fluoride crystal. Here is the beam of helium atoms reflected at an angle equal to the angle of incidence, and on either side of this, they found these beams of diffracted helium atoms. The wave-like properties of neutrons also show up when they are diffracted from crystals. Whenever the momentum of the neutrons gives them suitable wavelengths. Here are pictures made by beams diffracted by a crystal of sodium chloride, a crystal of common salt. The picture on the left was made by X-rays. That on the right was made by neutrons. Today, the wave-like behavior of material particles is well established. Indeed, it forms a foundation for our way of understanding matter. The behavior of individual atoms and the ways they join to form molecules defied explanation until the wave-like nature of their electrons and nuclei were discovered. Nowadays, atoms and molecules are pretty well understood, but an account of that would need a film all its own. And the fact which Larmor helped to discover, that a beam of particles behaves like a beam of waves with the wavelengths de Broglie predicted, is used in countless researches. Here, Larmor is really turning the Davison-Larmor experiment upside down. Instead of using the reflection from crystals to prove that electrons behave like waves, he uses their reflection today with confidence that the electrons will behave like waves. Since he can trust it, he uses it to find out more about the arrangements of atoms that are reflecting the electrons.
That's enough. 8 times 10 minus 7. You see this popped it off?
Well, that was an interesting video. I liked watching that. Let me just jump back over here. While I was watching that, Noah asked, "Do you have an intro video for this?" Yeah, if you go to my channel, I have a playlist where I've been putting all these videos, and the very first video in that playlist, the first one I did, I do explain why I'm doing this and what I'm doing. So if you're interested in watching that, you can go there. If you want to read, you can go to my blog. And it should be in the in the most recent articles. I posted an article about this. I'll probably get everything compiled together once the challenge is done. I've just been a little bit busy doing this right now to fully post everything and collect everything about it. So I'm going to go on to question 1.5, which was related to that video that we just watched. And let me just get back over here. Work on this. So let's go. Question 5. All right. Watch the video of matter waves. Done. Okay. Explain using diagrams and or equations why there are diagonal lines in the diffraction pattern which appears at 12:59 in the video. Okay. So here we have, let's say they're little holes. And so what would be the right way to draw this? I'm really running low on erasers here. Every single one of my pencils is all its own erasers. So you can tell I'm making lots of mistakes because I've had to use the erasers quite a bit. So we have some kind of like, it's a grading in both directions. And so I will draw it like this. All right, so each of these produce kind of it's like a spherical waves. And then let's say I'm just gonna, in an abusive perspective here, I'm just gonna angle this way. And so we have our central spot. Let's say the electrons are coming through here. Our central spot, we have our two, these correspond to the horizontal interference. And this is the, oh, this is the vertical, so oops, vertical interference. This is the horizontal interference. And how do we explain these guys here? I think it's going to be because of the interference between these two and these two and these two and these two that we're going to get that. So with this one here, we have this grading, whereas here we have the diagonal lines. Oh, that's really cool, Noah. Yeah, let me know how it goes. It's math is a long journey, and you know, sometimes you have to go back and relearn some things. I'm definitely finding there's some stuff here that it's like, wow, it's been 8 years since I've done a lot of this stuff. A lot of it's rusty, a lot of it's needs to be refreshed. But as long as you keep at it, you can get there. Yeah, so I'm just gonna do my really lack of elegant wave here. Is the diagonal spacings in the crystal lattice. That's my guess. All right, I'm just going to go on to C because I don't think that needs to be checked. In their classic experiment, Davison and Germer directed an electron beam into a nickel crystal in a 90-degree incidence and placed a detector at an angle theta from the beam. Okay. When the electrons are excited by a voltage of 54 volts, they have a strong reflection. The angle theta is 50 degrees. Using the de Broglie relation and the Bragg relation, compute the lattice spacing in the nickel crystal. How does this compare with the value of 0.215 nanometers measured by X-ray diffraction experiments? All right. So maybe I'm going to want to go back up and do 4 first. Because let me just draw this experiment, and then I'll go back and do 4 because that's going to be related to this. So they're shooting at this nickel crystal here, and it is at theta, detector theta from the beam. So at 50 degrees, there is a strong. So this is where our interference patterns collide. Oh, and this is where it's strong. And what is this, 54 volts? So what's happening here? Well, I think this is the same idea as before that we're going to have. Let me try to draw a better diagram. So let's say we have our lattice here. I'm going to draw this as an actual lattice. So if we have it, this is like the gap, right? So it's kind of like each of these guys is giving off and then going directly back, you'd have constructive interference, and then going 50 degrees off this at a long distance would correspond to no, not like that. It would be, that's the wrong way to draw it. Let me try drawing it again. So 50 degrees, let's go here. So this is the same, and then this is 50. This is theta, let's go 50 degrees. And this is one wavelength more than the it's one wavelength more than the spacing, right? So this is kind of the same question as the last one. Yeah, I'm gonna have to make sure Fortunately, I don't really have room to show both pages at the same time. So I'll just try to recopy things. So what's the right way to think about this? "50 degrees off of the incidence here." Looks like this. Is where our second maximum is. And it's the distance like, doesn't it depend on D? This is exactly one wavelength more than this guy. So I guess this is the thing that's controlling this right here, this triangle. So this one we have theta, or the wavelength of the electron. This one we have the spacing. And what's this one going to be? Well, if this angle is theta, then what's this angle going to be? This is theta. So if this thing is theta, then this is 90. Let me draw this triangle again. Yeah, this was the right way to think of it. Oops. And I'm not drawing my triangles very good these days. All right. So this is lambda. This is d. And I'm going to call this thing, because the d, if this is far enough apart, these are almost parallel. So I think that's the d far away simplification. This is theta. So by this is halfway between. This is 1/2 d, 1/2 d. So this one we can say is also theta, right? Yeah, because of similar triangles. This one's 90. It's 1/2 d. So we have an angle like this. This 50 degrees. Therefore, this is 40 degrees. This is lambda, and this is 1/2 d. So what is the lambda for our what's the lambda for our thing? So we have momentum is equal to h over lambda. So our momentum of our electrons, what's our momentum of our electrons? It's mv. One sec, I'll just switch this over. So lambda is equal to h over momentum is equal to h over mass velocity equal to mass. How do we figure out the velocity from the voltage? It's the 54 volts. So 54 volts is going to give our 1/2 mv squared is equal to the 54 times QE, I think. So V is going to be equal to the square root of 2 times 54 times QE divided by mass electron. And 8 times QE over mass electron. So our wavelength is going to be h is equal to, so this is 2 pi times h bar. Let's just see if this makes any sense first before I do this. So this is equal to meters. So I'm just going to put this as meters is equal to h bar is kilograms. This is joule seconds. I'll write it as joules seconds first. So joules times second times, I'll just put joules times second times kilograms, and then this root is 108 is volts, which is joules per coulomb times coulomb over kilograms in joules is equal to force times meters, which is equal, or newtons times meters, which is equal to F equals ma, so that's kilograms meters divided by second squared. So this is kilograms times meters squared times second minus 1 times kilogram minus 1 times coulombs cancel, and we have kilograms over kilograms. Kilograms, meters. Meter squared, second squared, cancel. This is going to cancel this guy. This is going to cancel this guy. And this is going to turn into a 1, and we're going to cancel off one of these. And so, okay, so we got the right units. And so our lambda here is H bar. Electron volts per second. Now I want I don't want it in that form. I want to convert it. This is just H though. Yeah. So I don't need the 2 pi. So I'll go 6.6 10 to the negative 34 joules per second divided by mass of the electron, which we did in the last question. .111 times 10 to the negative 31 all over square root of 108 times 1.6 times 10 to the negative 19 divided again by 9.11 times 10 to the negative 31. So let's simplify this a little bit. We've got negative 31 is going to be plus 31 minus, so let's go, let me just write this here. 6.6 10 to the negative 34. 0.11 times 10 to the negative 31. And we got 108 times, let me just do this quickly on calculator. 108 1.6 9.11 18 9, so that's 19. So 19. So if I drop the 10, this is going to be 31 minus 19, which is going to be 12. 13. And so 1.9. Let's do 6.6 and 9.11. 32. So it's equal to 7.2. And we have right here -3, but it's now one smaller, -4. So I'm going to go 10 to -4 divided by the square root of 1.9 times 10 to the 13. So let's go. Oh, where's the square root here? Nope. 1.9 square root 1.3. So we'll go. So we get this out. This is going to be 5.5 equals 5.5 times, this is 10 to the -4 minus 10 to the 6.5. So that's minus 10. 10.5, I think. 5. So what's 10 to the power of 10.5? So it's 10 square root. Oh, it's square root of 10. 3.16. So we'll divide this by 3.16. So see. 3.16. -10. And this was our lambda. Oh, I missed that. Noah asked, do I still do computer science stuff? Not as much as I'd like. I do like to do programming, but these days I haven't done anything super complicated, which I really like doing it, but I just, it hasn't been factoring as much into my work. So I think at some point I'm going to try another computer science project, get into doing something else. But I think at this point I'm at right now, I'm mostly doing just, small little apps. I sometimes use it, but I never feel like I'm really doing the kind of interesting computer science stuff. It's just usually just little scripts and things like that. -10. And what would that mean for D? I think this is going to be too small. What is the, oops. .215 nanometers. Okay, maybe. No, we're not that far off. And this is also 1/2, right? So if we have, this is going to be 40 degrees. So cosine of 0.5, 0.5 d over lambda is equal to cosine of 40 degrees. Opposite over adjacent, right? So 0.5 d over lambda should be equal to yeah, simulation stuff is very cool. I think definitely like doing the MIT challenge spent a lot more time on math and stuff than working with a lot of practical applications. So I'd like to learn a few more libraries for working with visual things, particularly with Python, because then you can do kind of cool stuff with it. I've mostly been doing just little things though. I've done a few programming projects since, but I haven't done as much as I would have liked. So this one here, we got this. So let's go times 2, so we got 2 cosine 40 degrees times this 1.74 times 10 to the negative 10. That seems to make sense. So this is going to be equal to, what's the cosine of 40 degrees? I should probably know this. Oops. 0.76. So times 2 times 1.74. It's equal to 2.6 times 10 to the negative 10. Which is equal to 0.266 nanometers. I mean, that's pretty close. It's pretty close. Yeah, the key was setting up the triangle this way. I forgot that this is how you're supposed to set up the triangle. So let me just go do question 5 and see if I got that right. And then let's go over to doing question 4 again, which I should be able to get now. This is 4, where's 5? Yeah, for just watching the video. Yeah, let me just, okay, so this was right. Although their graph of it was a lot better. Sine theta. I put cosine theta. Oh, right, because this is 50 degrees. I did 40 degrees, so I did do that, right? Oh, this is the Bragg relation. N equals 1, theta equals 50. NH over sine theta. I maybe just simplified it too much, I think. That's maybe where I'm losing the precision, because I'm very close to this answer. Where did I get? Let me just see what I have for here. This is h bar over 2qm mass delta v. Yeah, that should work. Because this is going to pull this down and pull it into the square root. So that should be right. And then this pi 2d sine theta, but theta was 50, so it should be the opposite. I think this is right. I think I just maybe didn't use enough significant figures or something. Because I did a lot of calculating here, and I maybe just simplified it too much. So I think that that's probably close enough. This is actually 2.18 centimeters. I have not been super precise with the quantitative stuff here, so that's probably the reason. So let's go back to 4, or 1.4. I'll cross this off the list here. Go back to 1.4. Because now I think I should be able to get it, because it took me a while to figure out what was that Bragg relation. Okay, so adjacent interference patterns, blah, blah, blah. So this right here was the key, is that we have this triangle, like this. And so the angle theta, we already worked this out. This is theta, this is not 1/2 d lambda. So we have, we can do, yeah, sine theta now because this is opposite over adjacent. I don't know why I flipped it around that way. So 2 sine, so we have sine of theta is going to be equal to opposite over adjacent, which is going to be 1/2 d over lambda. So sine theta, lambda sine theta. Do we know what the d is? We want to find between adjacent maxima. So this distance, well, this is d. And this is what? This is the angle. This is theta. So hold on a sec. We've got this angle here. So our theta, and this is big D. This is our omega. Yes, no, this is not right. So momentum P. So P is equal to H over lambda. So lambda is equal to H over P. So we have 2H over P sine theta is equal to E. And then sinus, this is opposite over adjacent is our tan. So tan of theta is equal to omega over big D. So opposite over adjacent is equal to omega over D. Can I make this work here? think I can do the same thing, right? We have dp 2h sine theta. Oh, how do I do this again? So if you have the opposite over hypotenuse is our sine, so the what's the right way to, oh, this is equals to, equal to opposite over hypotenuse, tan is opposite over adjacent, same angle though. Sine theta is equal to, that's dp over 2h, so they're both equal to sine theta. And so if we square both sides, we have m squared plus d squared is equal to e squared p squared over 4h squared. I don't know. And divided by this is equal to this, right? So I've got square the over squared for squared. Yeah, v squared. Minus this is going to be oh god, this has got to simplify some way. I'm missing something really obvious. I did something awful with this tan function here, which I shouldn't have done, I think. What's the tan in our problem here? What's the height of this thing? Hmm. I've done something horribly wrong. Let me go back to my thing here. So this is our W. This is 1/2 D. This is lambda. This big thing is D. And so what we can just do by similarity relation that 1/2 D is to lambda These have to be proportional, right? What is d minus d? That might be helpful. D minus d squared. Let's square anything, 4 lambda omega squared, 2 little d squared. Right? So let's do it up here. The width of the slits is much less than the de Broglie wavelength. So if we take the width of the slits to be much less than this, and also this is going to be equal to approximately big D minus little d is going to be this d squared is going to be negligible. So this is going to be 2 root lambda. That seems suspect. What is our lambda? I think we calculated it. Lambda is equal to I'm doing something wrong here. Hold on one second. I'm trying to keep it on. Are you trying to keep it on? Are you trying to keep Milky out of the room? Yeah. Oh, sorry. He's scratching. Well, I have done something wrong here because we should expect to see some dependence on the gratings. I mean, we've got them up here, but Let me try it again. So we have, this is the situation. All right. This is our omega. This is our D. This is our lambda. This is our sine theta. Do we know this is 1/2 of D? Where did I get the 1/2 of D? I think I did that from somewhere else. Oh yeah, this is because this is just arbitrarily from the center point of those two. Okay. I'm trying to solve for W. And we know that lambda is equal to H over this. I guess we just need P because we've already got P. We don't need, momentum. And then this is also equal to opposite. That's going to be right? This guy's going to cancel out this. P is going to come up top. It's going to be PD H pi. We're going to square everything. It's equal to pi H squared plus I'm getting the same answer. All right, I'm gonna check it out. See what I might be doing wrong here. Let's go up to 4. This is 4. 4. Okay. D sine theta m is equal to m lambda. So if we take for m equals 1, this is d sine theta is equal to m. This is equal to lambda. So we have sine theta is equal to why do I have it the backwards way? Sine theta. D. And so which is equal to lambda over little d. Now, what did I screw up to get this complicated mess? Well, I think for one, we can consider this angle here. And I don't think it loses any generality, right? Because I don't think that that matters. So what would that look like? So we have make over D. Because this D has to be the Do they have a drawing? No. HD or P little d. I feel like there's some trigonomic substitutions that are happening here that I'm missing. What did I do in my notes the first time around when I did this problem? Did I draw the graph? I don't know how to get this. All right, I think that's probably enough for this question for right now. I will look at this again later. Let's go to the second part. B. Experiment performed by Johnson in 1961. Electrons were accelerated through a 50 kilovolt potential towards two slits separated by a distance of d. It's 2 times 10 to the negative 4 centimeters. D 35 centimeters beyond the slits. Calculate fringe space. So 50,000 volts. .6 times 10 to the negative 19. I think that's what we did before for the electron. Coulombs is equal to our energy, which is going to be 1/2 mv squared. multiply this by 2, and we're going to have 110 to the 5th. Mass of an electron, which is, what was it, 9.11? 10 to the negative 31. I think that's what it was. Yep. So plus 19, this is 24, minus 31 is going to be negative 7. And this is 9.11 divided by 1.6. So what's that? The square root of 5.6. And this is 3.5. No. I've done something horribly wrong. It should be going much faster than this. What have I done? Volts is equal to joules per Coulomb. All right. No, this is too high. Right. Times 1.6 times 10 to the negative 19 coulombs divided by 0.11 times 10 to the negative 31 kilograms. Dimensional analysis joules is kilograms, meters per second squared divided by kilograms, meters per second. Okay. So, and I had a 2 here. I had to times it by 2. So this is going to be, 10 to the 5th. Get this back here. All right. And we're going to have 31 minus 14. 31 minus 14 is going to be 17. So we're going to have 10 to the 17, which is going to be let's just do 1017 first and then get this all sorted out. So 1.6 divided by 9.11. Oh. All right, so we got 1.8 times 10 to the 16. It's 1.8 times 10 to the 8th meters per second. It's very close to the speed of light. I don't know whether that's going to make any difference, but all right. And then so the momentum is going to be this times, so P is going to be equal to 1.8 times 10 to the 8th times 1.6 9. So 9 minus this is going to be 22. 22. 22, and this is going to be kilograms meters per second. And then what is our relation here? What do we want to find out? So lambda is going to be equal to 2 pi h bar, which is 6.6 times, what did I figure for the, what was h bar? H 6.6 and 10 to the negative 34. That's kilograms meters squared per second divided by negative 22 kilograms meters per second. You're going to get meters, which is right. And so we have 2 pi 6.6 divided by 1.6 times 10 to the, subtract 22 over here, should be 10 to the negative 12. But what's this first? Because that's going to add some. So 2 times pi times 6.6 divided by 1.6. Going to be, so this is going to be 2.5, 2.6 times 10 to the negative 11 meters. And then what is the all right. W from the last problem is going to be equal to lambda d over d. It's going to be equal to 2.6 times 10 to the negative 11. And then this is 35 centimeters, so 0.35 divided by 2 times 10 to the negative 6. So this could be, let's just put 3.5 divided by 2. Then we're going to have this as negative 4 divided by that. So we're going to have times 10 to the 4th. This is going to be equal to 1.75, 2.6 times 1.75, 10 to the, oh, this is too small. This seems way too small. (10⁻⁷). That seems way too small. Where did I screw up the calculation? Well, let's just work it out regardless. 2.6 times 5. Way too small. Way too small. Did I not write something down here properly? Oh, this is 35. 35. So this is an extra order of magnitude. So this is 10⁻⁶. Still seems way too small. Oh, let's see what the answer was. 5.49 times 10⁻⁻12. I got 2.6 times 10⁻11. Where am I missing something? Did I do something wrong? Oh, right. I used H bar, and this is H, not H bar. Okay. So the answer was 5.49 times 10⁻12. And so this was about 9.6 times 10⁻⁷. Yikes, that seems really small. Oh. Visible light. So visible light has 400 to 700 nanometers, yeah. So let's take what's the split of that? 550 equals 5.5 times 10⁻⁻what? 7. So we're 5 orders of magnitude, 4 orders. Yeah, 5 orders of magnitude smaller. So everything would have to be bigger by 5 orders of magnitude. No? So this is 10 to the 5th higher. So we need to make this. What are we trying to scale here? We're just scaling everything up by 10 to the 5th? No. Scaled up. I mean, everything just multiply by 10 to the 5th? Is that what we're doing here? So D would be 35 centimeters. So that's 0.35 times 10 to the, times 10 to the 5th is, 10 to the 5th meters equals 3.5 kilometers. And D would be, so it was 2 times 10 to the negative 4, so it's 20 centimeters, and fringe spacing is going to be roughly negative 6, 10 centimeters-ish, like that. It's 10 to the 6. All right. I got these ones right, I guess. Yeah. Okay. All right, this one, I feel like I got this question wrong just because I'm missing some kind of mathematical substitution here. All right, I'm going to cross this one out for right now. And yeah, I still got some time. So let's go on to 1.6 and see what we can get for that. Oh, this is the single slit diffraction. Oh, so I remember the key to this one being, because I was thinking originally that, oh, you're going to have to integrate, but you don't really actually have to do that, because what is the idea here? We're going to consider 2 points. Now, how does this work? Estimate the width of the pattern observed from the screen. So what was it? If we were going to take, what was it, half of this distance? It was the same idea as the last one, I seem to remember. It's when these two guys are out of phase. So when this thing is at 1/2 lambda, now they're going to be out of phase for this angle, right? And they will be for all of the ones on this angle. And if we're assuming they're really far away, these are all going to be approximately the same angle. Can I make the same argument I did last time about it being half? How did I get that half? I don't think so. I think this has to be theta right here, right? I think that works that way. A, B, and C have to be 180. B is 90, so C is C equals C plus A to 90. I think I can do this. I'm really looking for theta with W. Okay. I think this is going to be the same thing, but just with pi by 2. So sine theta is equal to 1/2 lambda over 1/2 dx is equal to lambda over dx delta x. And so I think this was the same idea we had with the last one. So what was our logic? I lost my head. Sine theta equals W over D. It's going to be half the wavelength, so half the distance. So I think it's going to be this much, right? Let's see if that's right. Yes, I think there must have been small angle approximations in that last one, which I missed. All right. In the photon picture of light, the light beam after the slit comprises a large number of photons. The range values of transverse momentum. So the transverse velocity would be, well, it would be the distance they covered over time. What's the time? Time is equal to d divided by c. So we have it equal to that's the transverse velocity. We wanted momentum. I think it's just proportional to this, right? Doesn't bring an h bar here. What's the units? This length is dimensionless. And then we know that momentum is equal to h over lambda. This can't be right. I don't have the right dimensions. That's W over this P. This is right. Right. Yeah. All right, that was actually fairly easy. C. Since we know the photons, each of the photons went through the slit, we have effectively measured the x position of the photons at that point. So oh, this is just this form now. And then dx p, but this is equal to dx times what do we have? What was the width? And d over dx divided by d Cancel, 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 cancel. We have 9p is equal to h. That's kind of nice. All right. All right, so I will cross this off now. So problem set 1 is more or less done. I'm going to just see if I want to put anything else up there. I don't think so, because I think it's just, I think it was just small angle approximation stuff. I'll revisit that if it's something that is showing up in one of the midterms, but I think it's fine for right now. All right. Let's now look at some of the other stuff we have. So do I want to go forward? You know what? I might leave it off for right now. It's been about 4 hours, so I think I'm feeling pretty good right now with the progress I'm making. I'm going to be back at it tomorrow. I should be able to work a bit more tomorrow, so hopefully I can chew off more of these problem sets than I was able to do today and get through a big chunk of these. I'm going to try to focus on some of these ones that I've circled. I might wait to do anything involving crystal momentum, which I think would have only been potentially problem set 10, just because I didn't cover that fully. So tomorrow I think I'm going to do problem sets all day, kind of like how I have been doing. I mean, I've been struggling with some things, but it's partially just the process of reacquainting myself with a lot of earlier concepts. This whole thing with the electron orbit, just some differential equations that are just a little bit granular. So I think, did I add? Yeah, I put differential equations on the to-do list for concepts. So I might tackle that again. So this is sort of the process of taking some questions, figuring out what's I don't understand, what's weak, doing more questions. So I think this second iteration of the problems is going to be pretty good. It's just going to be a question of how much time I have to improve on those things and whether I'm going to get to the point that I'd like to get at the end of this. I mean, it's definitely been more challenging than I had anticipated, and some of that is just getting reacquainted is taking a little bit of time, but a lot of it is just the class itself. I mean, definitely this problem set 1 is a lot of earlier physics, but from some of the later things here, this is all new. So this is just the difficulty of the class. So I'm going to keep working on it, and I will be back tomorrow to work on it again. And we'll just see how far I can get in this week. And then after that, I'll just sort of focus on exam prep.